Okay, this is the second part of lesson 5.2, and basically what this lesson is about is they're going to show you how to integrate your other trig functions. Right now, really the only trig functions that we know how to integrate are sine and cosine. So this is going to show you how they came up with the antiderivatives of the rest of those trig functions. Okay, so the first one we're going to start with is the integral of tangent x. So if I were to look on my sheet of derivatives and integrals, this wasn't on our list yet. Okay, and the reason it's not on our list is because this is going to include a natural log. Here's why. First of all, I have to rewrite tangent x as sine x over cosine x. Because as it is right now, I don't know what the antiderivative of tangent x is. There's not one. So I need to rewrite it. On this one, I can say, okay, I'm going to use u substitution. And if I let u be cosine x, du is negative sine x, which I have pretty much except for the negative. Okay? So we know that if I have my u, I have part of my du, there it is. And I need a negative here, so I need a negative here. Okay? Now I'm going to rewrite this. This is negative the integral of 1 over u du. Okay, well that's really easy. It's negative natural log of the absolute value of u plus c. And now I'm going to substitute my u back in. Negative natural log of the absolute value of cosine x plus c. So now anytime you see the integral of tangent x, you're going to know it's negative natural log of cosine x plus c. Okay, so this is one that you're probably going to want to memorize. If you don't want to have to memorize it, you can always derive it from doing the u substitution integration. All right, so let's do another one. Cotangent x. So it kind of makes sense that we're going to set this up the same way. Cotangent x can be rewritten as cosine x over sine x. So it kind of makes sense from my other example that we're going to use u substitution, and my u is sine x, which means the derivative of sine x is cosine x. So now I'm going to rewrite the problem. So now I have, remember, here's my u, here's my du, so everything matches up all nice and neat. 1 over u du. So now when I integrate that, it's natural log of absolute value of u plus c. Substitute your u back in. U is sine x plus c. So when I integrate cotangent x, it's the natural log of sine x plus c. Okay, let's do another example. Example 3, integrate tangent 7x dx. Okay, so first of all, it involves tangent. So anytime it involves tangent, I know I need to rewrite it as sine 7x over cosine 7x. Okay, so my u is cosine 7x. The derivative of cosine x, we already said, was negative sine 7x. But then this is kind of like that peanut M&M, or the, I'm sorry, the M&M. This is the chain rule. So the derivative of cosine 7x is negative sine 7x times the derivative of my u, so times 7. So really that's negative 7 sine 7x. So let's look and see if it all matches up. Okay, here's my u. Here is my du, and the only thing I'm missing is this negative 7. So I can put the negative 7 out in front, but the negative 1/7 has to go in front. So I'm going to rewrite the problem. Negative 1/7. There's my du on top, so 1 over u du. When I integrate that, I get negative 1/7 natural log of u plus c. Substituting my u back in, negative 1/7 absolute value of cosine 7x plus c. Okay, let's go to example 4. All right, example 4. So let's try using u substitution. If I say u is tangent x plus 5 du, so the derivative of tangent x is secant squared x. 5, the derivative is just 0. So that works out really well. Here's my u, here's my du. Everything matches up. So here's my new problem. The integral of 1 over u du. When I integrate that, natural log of the absolute value of u plus c. Substitute your u back in. Tangent x plus 5 plus c. So far, so good. Okay, here's kind of a tricky one. Secant x. We don't know what the antiderivative of secant x is yet. All right, so in order to do this problem, I can't let u be anything. I don't want to say 1 over cosine x because the derivative of cosine with negative sign, I don't have a negative sign there. So I can't rewrite it as 1 over cosine. So I have to multiply secant x by a form of 1. Okay, and what I mean by that, I can multiply anything by 1 because it doesn't change its value. So I know this is going to be really weird, and for you to see it the first time, I wouldn't expect you to know to do this. Okay, I'm going to multiply this by, let me write it down and I'll say why. Secant x tangent x. But here's the thing, if I multiply the top, isn't this just a form of 1? Secant x tangent x over secant x tangent x, it's just 1. So I'm multiplying secant x by this form of 1. Okay? Now, here's why we're going to do that. If I go ahead and distribute that secant x, well, I don't even have to distribute, I'm just multiplying. Secant x times secant x is secant squared x, and I'm sorry, that should be a plus sign in between there. Secant x plus tangent x. So I'm going to distribute my secant x. So that's plus secant x tangent x all over secant x plus tangent x. I keep forgetting my plus sign. Dx. Okay, so now let's try u substitution. If I say, okay, I'm going to let u be secant x plus tangent x. Okay, well, what's the derivative of secant? The derivative of secant is secant x tangent x plus, what's the derivative of tangent x? It's secant squared x. So look how nice that matches up. Look, here's my u. The derivative of my u is this whole thing right here. The whole thing is du. So now I can rewrite the problem. This is actually just 1 over u du. And when I integrate that, whoops, I lost half my, there we go. So that's going to be natural log of absolute value of u plus c. Now I'm going to substitute my u back in. Natural log, here's my u way up here, secant x plus tangent x plus c. So anytime you want to integrate secant x, you can go through this huge long process, or you can just memorize that. Okay, let's do another one. Okay, this is a definite integral, so I know I'm going to be evaluating. Let's figure out what my u is going to be. So if I say u is theta minus sine theta du, so remember theta just takes the place of x, so the derivative of theta is just 1 minus the derivative of sine is cosine. Well, that makes it all really nice. There's my du, here's my u. So first of all, I know I'm going to rewrite this as 1 over u du, but I need to figure out what my new upper and lower limits are going to be. So we know how to do that. Okay, I'm going to plug 2 in my u, so I have u of 2 equals 2 minus sine of 2. Now that looks really weird because we're used to seeing like sine of pi over 6 or the sine of 30, not the sine of 2. So instead of trying to figure out what that is, we're just going to say that's 2 minus the sine of 2. That's my new upper limit. Let's do our 1. Let's replace our 1. So that's going to be 1 minus the sine of 1. So even though it looks weird, we're going to go ahead and go with it. 1 minus sine of 1. So we have our new upper and lower limits. Well, let's go ahead and integrate. So 1 over u is going to be natural log of absolute value of u from 2 minus sine 2, 1 minus sine 1. Okay, so now I'm going to take each of these, plug them in. So I'm going to do my top one first. So I have natural log of 2 minus sine 2 minus natural log 1 minus sine 1. You can leave it just like this, or we know that using properties of logarithms, that a subtraction problem is really division. So I could write it like this as a single logarithm, natural log of 2 minus sine 2 divided by 1 minus sine 1. Those are absolute values. I could just put it like that, absolute value. So either one of those would be okay. All right. Example 7. Now on this one, can't let my u be x because the derivative of x is just 1. So my big clue here that this is my u is I have something raised to a power. So let's try it. U equals 1 plus natural log of x. The derivative of this, derivative of 1 is just 0. Derivative of natural log of x is 1 over x. Do I have that? Yeah, here's my u. 1 over x, there's my du. So now I'm going to rewrite this. It's u squared du. Let's find our new upper and lower limits. So I have u of e, which is weird, but e is just a number. That's okay. I'm going to plug e in. 1 plus the natural log of e. Okay, well, one thing that you should remember is that the natural log of e is always 1. So now I have 1 plus 1, 2. So my upper limit is 2. Now I'm going to plug 1 in. U of 1, 1 plus natural log of 1. Okay, the natural log of 1, we should know is 0. So I have 1. So my new lower limit is going to stay at 1. So now I'm ready to integrate. When I integrate u squared, it's u to the third over 3 1 to 2, and I just plug those numbers in. 2 cubed over 3 minus 1 cubed over 3. That's going to be 8 thirds minus 1 third, 7 thirds. Okay, and I think we have one more and we are done. Okay, so this is just a little reminder about the second fundamental thermocalculus, that second part of fundamental thermocalculus. It says let f of x equals the integral from 1 to x of 1 over t dt. Then I want to find the derivative of the antiderivative. So remember, integral is the same thing as antiderivative, and I want to find the derivative of that. Do you remember what you do? Remember, we like these because there's no math to do. I just take, as long as it's a constant to x, I just plug my x in. That's it. So this is asking the same thing. It's giving me, remember, capital F stands for the integral or antiderivative, and I want to find its derivative. So I just plug it in, 3x, but this time, since it's not just a 3x, I mean an x, it's a 3x, I multiply that times the derivative of 3x. So my answer is, my 3's cancel, 1 over x. Okay, I think, let me check, that is it. All right, I will see you, or actually, I will put your assignment